In this video, I will be showing two examples on a common physics problem where something is hit from a cliff and it's a projectile motion, and then it hits the ground, and you need to find stuff like the range, maximum height, sometimes even the final velocity before it hits the ground. So let's start with this first question. An astronaut on the moon, where the acceleration of gravity is 1.6 meters per second squared, strikes a golf ball, giving the ball a velocity of 32 meters per second, 35 degrees above the moon's horizontal. The ball lands in a crater floor that is 15 meters below the level where it was struck. Determine A, the maximum height of the ball, B, the time of flight of the ball, and C, the horizontal range of the ball. So the first thing that I'm going to show you is just a diagram of what this even looks like. An astronaut on the moon strikes a golf ball. Here is the golf ball. And it says it's giving the ball a velocity of 32 meters per second, 35 degrees above the moon's horizontal. So what the angle means is that if the ball is flat if the ball is flat like this, then there's going to be an angle that it is kicked at. Like, it's not just going to go straight like this, because the ball is getting striked at this angle right here. This angle here is 35 degrees. And when it says a velocity of 32 meters per second, this velocity, this is a total velocity, which means it's just the velocity here. Now, to do these sort of problems, something that my grade 11 teacher taught me was to use a chart so you can clearly see what do you have and what do you need. So here is a chart that I would recommend you to draw. In projectile motion problems, the kinematic equations that you've probably learned are only applicable to one dimension, so either like the x dimension or the y dimension. But in these problems, there's two dimensions. So what we want to do is to separate the problem into two dimensions. So each dimension will have its own displacement, initial velocity, final velocity, acceleration, and time. Okay, so if we look at the problem, let's start with displacement. So in the problem, it doesn't give you anything about the x displacement. However, here it says the ball lands in a crater floor that is 15 meters below the level where it was struck. So imagine this ball, it's going to go up and then it's going to fall down. And this distance of the cliff is 15 meters, since it is landing on the floor that's 15 meters below where it was struck. And the displacement is the difference between the final position and the initial position. So you might think like, oh, isn't the displacement like 15 plus this amount? Well, it isn't, because this is the initial position. Well, this is the initial position of the ball, and this is the final position of the ball. And as you can see, the difference between the final and initial position, which is this, is 15 meters. Okay, so we can start filling up this chart, but first let's determine the positives and the negatives. Usually in physics, right is positive and down is negative. That means if an object is going up, it's going to be positive, since going down is negative, and going left is negative, since we said that going right is positive. In this case, the ball is going to go down by 15 meters, so we have to add a negative and then 15. Okay, that means it's negative 15 meters. And the next thing we want to do is find the initial velocity for the x component and the y component. So let's start with the x component. The initial velocity of the x component is going to be how fast the ball is traveling this way. Because when it's in the air, the ball is going to go forwards. It's going to go forwards like this, but it's also going to go up like this. So what we just did, so then in total, the ball is going diagonal like this. So to calculate the initial velocity of the x component, we can use SOHCAHTOA. So adjacent to the 35 degrees, this is what we want, be initial for the x. And to get this, we can use cosine. So cosine of 35 degrees is adjacent over hypotenuse. So adjacent is what we need, and then hypotenuse is given, which is 32. So that's why I used cosine, since we're looking for the adjacent side and we're given the hypotenuse. So to rearrange this equation to get the initial velocity of x, just multiply the hypotenuse, which is 32, by cosine 35. So if you do this in your calculator, you will get 26.21 meters per second. And that is the initial velocity in the x direction. Now, it's also just useful in general to calculate the initial velocity in the y direction. And the initial velocity in the y direction is this part, since the ball is going up initially. And let's call this VIY. To do this, we can use sine. So sine 35 equals opposite over hypotenuse. The opposite side of 35 degrees is the initial velocity of y, and the hypotenuse, of course, it's just 32. And then solving for the initial velocity of y, it's going to be the hypotenuse times sine 35 degrees. So in any of these problems, if you want, you can just skip this step, since what always happens is that you'll have to multiply the hypotenuse by sine or cosine, whichever. If you're wanting to find x, it's going to be cosine the angle, and if you want to find y, it's going to be sine the angle. So if you want, once you get used to this, you can skip this step over here. Now, let's see what we get if we multiply 32 by sine 35. Yeah, okay, so I got 18.35 meters per second, and that's the initial velocity of the y direction. Now, does the final velocity of x, is it different from the initial velocity of x? Well, if you're not counting air resistance, there's basically no other force acting on the ball as it's going forwards. So if the ball is going forwards because something struck it, technically it's going to go forwards forever, since no other force is going to be applied. However, in real life, there's air resistance, and once it hits the ground, there's friction, so this is not going to happen in real life. But in the ideal world, and for these problems, we're just going to say that the velocity doesn't change, since there's no force acting on it. That means the final velocity of x is also going to be 26.21, since the velocity doesn't change. Okay. Let's see what else the question gives us. So the question says the magnitude of g is 1.6 meters per second squared. Now, g is just the force of gravity, and this force is going to act in the y direction, pulling the ball down. Without gravity, the ball will just continue going in this direction and not go down. So the ball is going down, which means we have to use a negative. And we can just put this here since it's acting in the y direction. Now we can start to solve the first part of this question, the maximum height of the ball. So whenever you have looking at these, you need to have at least 3 of these to get any other one. And right now for x, we only have 2, the initial velocity and the final velocity. But in the y column, we actually do have 3 things. So that means we can basically solve whatever we need to solve. And now, right now, this d right here is not going to help us because we are looking for the maximum height of the ball. Okay, so the maximum height of the ball is gonna be about here, which means we have to change things a little bit. So now that the initial position of the ball is here, and the final position of the ball is going to be right here. That means we don't know the displacement because that's what we're trying to find. So let me just erase this. Oops. Okay, but now we know something else. We know that the final velocity of y is going to be 0. And we know this because imagine a ball is going up and is going down. Well, at this point, at its highest point, it's not going to be going up it's not going to be going down. It's just stationary. So to solve this problem, we're just going to make y, the final velocity of y, 0. Now, what are we trying to find? We're trying to find the maximum height of the ball. So which one of these would it be? Well, it's going to be the displacement. And once we find this displacement, we can add it to 15 meters to get the actual maximum height. So in order to do this, we need to use a physics formula. And you should be given 5 of the main ones. And what you want to do is look for a formula that has, in this case, we want a formula that has all of these and also this as well. We don't need to have a formula with time because we don't have the time and we're not looking for the time. So if I just look at my physics sheet, the formula that I used is V final squared minus V initial squared equals 2AD. And this is all just going to be for the y component. We're not going to use the x components since the maximum height is related to the y. So VF, we can plug it with 0 squared minus 18.35 squared equals 2 times negative 1.6, and then the d that we're trying to find. 0 squared is nothing, and negative 18.335 squared is 336.886, and this is going to be 2 times negative 1.6 is going to be negative 3.2 d. And now just to get d, we can we can divide negative 3.2 from both sides. And once you do that, you should get 105 point, hold on. Yes, so actually, yeah, it's 105.277 meters. But the thing is, that's only the height from here. So this answer would be right if you're calculating the height from the initial. But if you want the maximum height from the bottom of the cliff, it's just going to be 105.277 plus 15 meters. Now let's move on to part B, the time of flight of the ball. So when it's asking for the time of flight, it's asking for the time from when it's launched to when it hits the ground. So now we actually won't need the maximum height of the ball to do this. Instead, we will need to use the actual displacement of the y component, which is negative 15. So usually in most physics questions, when it's asking for the time of flight of the ball, and the situation looks kind of like this, you just want to use this equation, which I'll write right here. D equals VI T plus 1 over 2 A T squared. This is a very popular equation that in most problems you can use this to find the time. And we're going to use this again for the y component since you really can't do anything if you only have two of these, which an x it only has 2 of the 5, and you need at least 3 to use one of these formulas. So let's just plug this in. Negative 15 equals 18.35 t plus 1 over 2 negative 1.6 t squared. So the way to solve for this is to use a quadratic formula. So let's just simplify this a little bit more. negative 1.6 divided by 2, that's negative 0.8. Let's erase this. So to use a quadratic formula, you just want to move all the numbers to one side, and then you want the other side to just be 0. So what I'm going to do is I'm going to move the negative 0.8 t squared to the left by adding 0.8 t squared to both sides, and the 18.35 t on the right, we're going to subtract that from both sides. And we can just keep the negative 15 here. Now on the right, it's just going to be 0. And if you recall, the quadratic formula is negative b plus minus square root of b squared minus 4ac over 2a. So let's plug this in. This is the first, I forgot what you call it, but this is A, this is B, and this is C. So negative is going to be positive, 18.35 plus minus square root of b squared. So once you square the negative, it's going to go away. Then you would do minus 4 times 0.8 times negative 15. So negative 15 times negative 4 is going to be positive. So we can just add that together. And I'm just going to do this in one step because it's easier to just keep it like this. But you can show more steps. And then 2 times 0.8 is going to be 1.6. Okay, so as you can see, there's going to be 2 answers. The first one is going to be if you use the plus sign here. And then the second answer you're going to get is if you use a negative sign. So let's try first with the positive sign. So if you do it with the positive sign, you're going to get a value that's around 23.733 seconds. Now let's try it with the negative sign. Let's call this T1 and T2. So I got negative 0.79. So let's think about this logically. Time only goes in a positive direction. Like you can't have negative time because you can't go back in time. So that means T1 must be the right answer. Now once you have the time, you can fill this back into the chart. So we solved it for the y. We used the y numbers here to get this number. However, you can actually also put it in the x part because even though the velocities, the displacement, and acceleration are going to be different for x and y, it's still going to arrive there. It's still, the ball is still going to arrive here at the same time for x and y. It's going to arrive right here at the same time. So because of that, you can just place it here. So this is your answer, 23.733 seconds for B. And if you want to round it to the correct number of sig figs, that's 2 sig figs, because in the question, 1.6 and 32, you want to round it to the lowest number of sig figs, but they both have 2. So if you do want to round it to the correct number, it would be 24 seconds. Now, we still have to find C, the horizontal range of the ball. This is the easy part because we're dealing with the x component, which doesn't have any acceleration. Whenever you don't have acceleration, you can use the formula d equals vt. And this will only work if you don't have acceleration, and as you can see, in the x component, there's no acceleration. So the horizontal range of the ball, this can be represented by d, the distance. Okay, so let's just plug some numbers in. V, well, it's going to be the same since there's no acceleration. And t, we can use 23.733. Like, you don't want to put 24 seconds because that's not the final answer, so it's going to not be precise. You want to have more decimal points in the intermediate steps and only round it to the correct number if it's the last step. Now, if you multiply these two numbers together, you should get 622.11 meters. And again, rounding it to the correct number of sig figs, it's going to be 620 meters. Okay, so here is the second question. A golfer is trying to improve the range of her shot. To do so, she drives a golf ball from the top of a steep cliff 30 meters above the ground where the ball will land. If the ball has an initial velocity of 25 meters per second and is launched at an angle of 50 degrees above the horizontal, determine the ball's time of flight, range, and final velocity just before it hits the ground. Again, let's start by drawing a diagram so we know what is going on. This is a similar situation where there's a ball here and it's being hit at an initial velocity. This time it's 25 meters per second. And the launch angle is 50 degrees. Again, let's start with a chart. And here we're going to have the x and y components, displacement, initial velocity, final velocity, acceleration, and time. So if you notice in this question, it's asking for the time of flight. It's not asking for the maximum height of the ball. A lot of questions, actually, it's just more simple to find the time of flight. Usually with the things that they give you, you just have to find the time first before you can find anything else. So again, let's start by filling this chart. It says it's 30 meters above the ground, which means the displacement from the initial starting point to right here, where it's the ball's final position, is going to be 30. And again, let's say right is positive, and down is negative. So the ball is going down, so it's going to be negative 30. Now let's find the components for the x and y initial velocities. Let's start with x, which is this right here. So I'm going to do it the quick way, which is you take the hypotenuse and then you look at what's the relationship of this side to the angle. So right now it's adjacent, and when it's adjacent, you just want to use cosine 50. And if I type this out in my calculator, it's 16.07 about. And as we know, the horizontal velocity is not going to change. There's no other force acting on it except the initial force where the golfer striked the ball. So then the final velocity in the x direction is going to be the same. Now, we can also find this part, which is the y component of the initial velocity. And I'm going to do it the quick way again, where you always take the hypotenuse first and multiply it by either cos or sine. In this case, it's sine, since the side is opposite to 50 degrees. Doing this in my calculator, I get 25 times sine of 50, 19.15 meters per second. That's around what I get. So we can just place this right here. And as you can see right now, we only have 2, which is the displacement and initial velocity, in the y component. But we need 3. So what other thing do we know? Well, we know the acceleration. Because this is on Earth, acceleration is always 9.8 down. So down is negative, so we'll make this negative. Now that we have 3, we can use the equation that is very commonly used to just get the time. Usually we'll just be using this equation to get time. D equals VI t plus 1 over 2 a t squared. And let's plug this in again, like as we did before. Let me erase this diagram to make more space. Again, we can simplify this. Actually, you know what? I'm just going to simplify this right here. Negative 9.8 divided by 2. That's negative 4.9. So moving for negative 4.9 t squared to the left side, you get 4.9 t squared, and let's move the 19.5 to the left by subtracting both sides, and then we'll keep the negative 30. And and this is all equal to 0. Again, we can use the quadratic formula. Negative b, negative negative is positive, plus minus square root of b squared. I'm just going to do this in my calculator. B squared minus 4 times 4.9 times 30, negative 30. And I got 954.72. I hope this is the right answer because I didn't do this question before. Anyways, 2a is 2 times 4.9, which is 9.8. And let's see what we get. There's going to be 2 answers again. Yes, okay. 5.1 seconds. And actually, if you do the negative one with 19.15 minus the square root thing, you're going to get a negative number. So let's just stop here and say that the time of flight is 5.1 seconds. Actually, now that I realized it, this is 3 sigdigs and 5.1 is only 2 sigdigs. So you should technically keep another one, but I already deleted it on my calculator and I don't want to do it again, but you should keep 3 sig figs. So let's put this into the graph that we made, 5.1. And it's going to be the same for both since they're going to arrive on the floor at the same time. Now the range, again, this is one of the easier parts of these questions because the x component doesn't have any acceleration. So you can just use the formula d equals vt. So v, it's 16.07 and t is 5.1. And if you do this, you're going to get 16.07 times 5.1, 81.957. And to round this to 2 sig fig, it's going to be 82 meters. And that's the range. And for fun, let's just add it right here, 82. Now we can move on to the last part of this question. Oh my goodness. It's the final velocity just before it hits the ground. So let's just draw a diagram of what it looks like. So the ball is initially starting here, and then it's gonna go right this, and right here, right before it hits the ground, it's gonna have a pretty big final velocity since there's Earth acceleration affecting it. And let's zoom in and see like what it really looks like. So again, in the x component, it's going to be traveling straight with 16.07 meters per second. And what we really need to calculate is this. This is the final velocity in the y direction. And what it's asking for, it's asking for this. This is a total final velocity of the x and y components, and you also need to get the angle here since velocity needs the number and the direction, and we can describe the direction with the angle. So now let's figure out how to get this number. As you can see on our chart to the right, we have almost filled everything up. The only thing we don't know is this, which is basically what we're trying to find. So now we can use a lot of different formulas since now we have 4 things. And you can choose which formula to use. And just for me, the one that I used is VF equals VI plus AT. But you can also use other formulas. I just think this one's the easiest one in this case. So VF equals VI, which is 19.15 plus negative 9.8 times 5.1. Let me do this in my calculator. And I got negative 30.83. So this is the final velocity of the y component. And now all we need to do is find the total final velocity. So let's draw the triangle again. This is going to be 16.07, and since it's negative, it's going to go down. And when we're finding the total velocity, we don't really need to worry about the negative signs. We just want to find the number. So we're looking for this. So you can use Pythagorean theorem for this, so first I'm just going to write absolute value since velocity is a vector. And you can do this by square rooting 16.07 squared plus 30.83 squared. Let me do this in my calculator and see what I get. Okay, so I got 34.767 around. And if you want to round that to 3 sig figs, excuse me, because hold on. Yeah, I made a mistake. So actually you should be rounding everything to 2 sig figs because here is 25 meters per second and you want to round it to the least number of sig figs given to you on the question. And I'm not really sure why, but we don't really care about this number, the number of degrees. We just care about everything else except that. So in this case, 25 has 2 sig figs, so we're going to round this to 2 sig figs. Sorry for not realizing that in the previous question. So to 2 sig figs is 35 meters per second. Now this is the number, but you also want the direction. And to describe that, we're just going to look at this angle. So to get that angle, we're always just going to do tangent. And I'm going to do it like this. Tangent of theta equals opposite over adjacent. So in this case, 30.83 over 16.07. And if you do this in your calculator, you should be pressing the inverse tan, and then 30.83 over 16.07. And that's going to give me 62 degrees. So theta equals 62 degrees. Oh my goodness. Yeah. Anyways, now you get the answer which is 35 meters per second. And the way to describe the direction is you go east, and then if you draw like a coordinate system here, it's angling towards the south because this is south. So it's going to be east and then 62 degrees south. If you want, you can also write this another way as south. And for example, you want to start from the south and you want to go to this. You want to start from the south and go to this. That's just going to be 90 minus theta, which is 28 degrees. So you can also write it as south 28 degrees east. Wow, my voice is really tired and I'm very thirsty. So I hope this helped you in some way. Thank you for watching and I hope you have a great day.